In this video, we're going to look at an application involving equations of lines that's very common for Algebra 2 that we try to apply what we learned in Algebra 1. Sometimes the applications are interesting, sometimes they're a little nonsensical, sometimes we just try to have them fit the bill in a simple way that we can understand them, even though in real life many things are not simple. So for this particular application, there are multiple parts to it, but let's get an idea of what is happening. So we have a contractor found that his labor cost for installing 100 feet of pipe was $30. He also found that his labor cost for installing 500 feet of pipe was $120. So when we talk about labor cost, we are not talking about the cost of the supplies. We're just talking about the cost for paying for the amount of time that the contractor was working. What we should also see is there is a relationship here. When only 100 feet of pipe is installed, the cost is much lower than when 500 feet of pipe is installed, which makes sense. You do more work, you get paid more. But because of that, when more pipe is installed, more money is paid. We have a positive increasing relationship here. So in terms of a linear relationship, which is what is being described in A, we're going to expect a positive slope. So for part A, we are told we're given a scenario if the cost in dollars is a linear function of the length in feet, write an equation in slope-intercept form for that equation, for that function. Let y represent our cost in dollars and x represent the length in feet. So a couple key pieces of information. We're told that this is a linear relationship, and we're told what our variables are. So anytime we see a cost in dollars, we know that's a y value, and anytime we see a length in feet, that's an x value. So what is important for us is that we were given two sets of those. We were told that 100 feet of pipe would cost $30 in labor. Well, that's the first x value and the first y value that we have. So we can label those as x1, y1 because those two values go together. The $30 occurred when 100 feet of pipe was installed. And in a similar sense, when 500 feet of pipe was installed, the labor cost was $120. So same idea. Here's an x paired with a different y, and we can classify those as x2 and y2. And we might not recognize it from this setup, but we were actually just given 2 points on our line. They're just not written like we're used to seeing as ordered pairs. So if you can't see it from this setup, then maybe the first thing we should do is show these two values as ordered pairs. And so our two sets of values that give us ordered pairs, the first set that we were provided was 100 feet of pipe and $30. So that would be the point, the ordered pair 130. And the other ordered pair that was discussed was 500 feet of pipe and $120 of labor cost. There's a second ordered pair, which is very similar to what we just did for the examples in the last scenario. If you know 2 points, you can find the equation of a line because with 2 points, we can find the slope of the line. So if we're going to find a linear function, the next thing we need to know is the slope. So let's use our ordered pairs to find the slope. So we have our slope formula, m equals y2 minus y1 over x2 minus x1. So calculating our slope, let's substitute what we are given, and we're going to have y2 is 120 minus y1, which is 30, over x2, which is 500, minus x1, which is 100. And for us, that is going to give us a result of m equals 120 minus 30 is 90, and 500 minus 100 is 400, which seems like a complicated fraction with large numbers. That is something we can reduce. So if we reduce this fraction, notice that both values in the top and the bottom involve zeros, so we can reduce by 10. If we divide the numerator and denominator each by 10, 90 divided by 10 is 9, and 400 divided by 10 is 40. So we have a slope of 9 over 40, and if you try to reduce it, you'll realize that those two values do not reduce together. So that is our simplified slope. Now that we have our slope, we will find the equation of our line using point slope formula, because we now know the slope and we know a point, actually two, but we know a point that the line goes through. So when you know the slope and a point, that is enough information to use point slope formula. So let's go ahead and get set up. So recall that point slope formula is y minus y1 equals m times x minus x1. So in this formula, m is always your slope. X1 and y1 is technically just a point on your line, so you know 2 points that are on the line. However, if you want to keep using the point that you called x1, y1, that's fine, but just remember it's okay to use either point to do this. So if we substitute our first point, we're going to have y minus y1 is 30 equals our slope is 9 over 40, and inside parentheses we have x minus 100. Okay, so continue on. Simplifying this, we need to distribute within those parentheses, into those parentheses. So we have y minus 30 equals 9 over 40 x, and then 9 over 40 times 100 is going to give us, 9/40 times negative 100 is going to give us a negative value, and 9 over 40 times 100 is going to be 90 over 4, which typically we want to keep fractions involved in here, but we are talking about money in this example. And in terms of money, a lot of times we do have decimal values. So if this 90 over 4 is a nice decimal value, I'm going to suggest that we go ahead and use it for future reference of calculating cost. So let's figure out what 90 over 4 is. Putting it into a calculator really quick, we get 22.5 exactly. So if the decimal is exact, it is safe to use, and it'll make our calculations a little bit easier than trying to deal with the fraction value. So for this particular example, let's have y minus 30 equals 9/40 x minus 22.5. And then when we solve for y here by adding 30 on each side, we are going to get y equals 9 over 40x plus 7.5. Now, that is a good equation. One last thing we could do, because again, we're dealing with monetary values, we could see if 9 over 40 is a exact decimal that we could also apply. Maybe it is, maybe it's not. If not, we'll leave it. But if it is a decimal that is usable, then we might as well be consistent in our equation. And again, using a quick typing into the calculator, 9 divided by 40 is an exact decimal. To 3 decimal places, it's 0.225. So again, we are calculating monetary amounts using this equation. We're finding labor cost with our variable y. So we could write this equation as y equals 0.225x plus 7.5. So just one last reiteration. Uh, Decimals are okay if they're exact. If they're not exact, we should really be using the fractional value so that we aren't rounding anything until we're finished. But these decimals are nice, so let's keep them. So we have a couple questions now. We've done the hard work. We have an equation. Now it's just time to apply it. So in this case, what would the contractor's labor cost be for installing 240 feet of pipe? Well, for us, what we need to recognize is when we talk about 240 feet of pipe, we are talking about an X value. And so we have an equation that relates feet of pipe installed to the labor cost. And so when we know that 240 is our X value, all we need to do is substitute 240 in for our variable X into our equation. So let's go ahead and give that a shot. Our equation said y equals 0.225 x, but our x value that we're interested in right now is 240. So let's substitute there with parentheses plus 7.5. And all we need to do at this point is simplify our result. Multiply first, add after. So if you multiply, you're going to get 0.225 times 240 is equal to 54 plus that 7.5. Go ahead and combine those two values, and we get y equals 61.5, which is great. It's a number, it's the right number, but when we talk about applications, these story problems, we need to interpret our solutions, our values that we get in the context of the problem. So we have y equals 61.5. We said earlier that y represents the cost in dollars for the labor cost. So 61.5 is a monetary amount, and we're going to write that in a sentence as the labor cost of installing 240 feet of pipe is, we're not going to put 61.5, we're going to put $61.50 because monetary values have two decimal places. Okay, so there's one way to use our equation to calculate what the labor cost would be. And we can also now interpret what's going on. So part C says you have a slope in your equation. Let's talk about what it means. And usually to talk about slope, it's easiest to talk about it in its fractional form. So even though we are able to write the slope as a decimal, if we revert back to the fraction, we'll remember that the fraction was 9/40. And in terms of interpreting this, we just need to remember where those numbers came from. When we calculated the 9, that came from subtracting our y value. And when we had the 40, which had been 400 before, we had calculated that using x values. And I'm saying that based off of our slope formula. So if you remember, our slope formula had said, our slope formula always says y2 minus y1 over x2 minus x1. So the number from the top is calculated from subtracting y values. The number from the bottom is calculated from subtracting x values. So the 9 is our change in y. The 40 is our change in x, and that lets us interpret our slope because it tells us how much the y is changing with this change of x. And so because y is our labor cost in dollars, and 40 is the feet of pipe installed, we're able to interpret our slope using those, using that same wording. And we can state this as the labor cost increases because it is increasing over time. The labor cost increases by $9 for every 40 feet of pipe installed. Now that is a little atypical to use two different values like that. When we initially talked about this, we did talk about rate of change going up for every 1 unit of installation. So I'll take back what I said earlier. We could interpret this using our decimal value as well, as long as we're careful about it. If we talked about the slope value of 0.225, we could say the same thing using different numbers here. We could say the labor cost increases by the slope value, this decimal value, is 0.225. So that is our monetary amount. So strange to put, but $0.22.5 for every 1 foot of pipe installed. Okay, both of these are actually saying the same thing. This is in a more standard way where we're talking about just 1 unit of increase. So for 1 foot of pipe, your cost is going to go up 22.5 cents. But how often are you just going to have 1 foot of pipe installed? So maybe something that makes a little more sense to us would be saying that something along the lines of labor cost goes up $9 for every 40 feet. Okay, so in these applications, when you do find your equations, use those equations to apply them to the other parts. Main thing is keep track of what your variables represent.